Hello, I am Ahmad, and in this video, we are going to talk about lateral torsional buckling. As we know, in many codes for designing a beam under the bending, we need to consider the lateral torsional buckling. For example, in Eurocode, we need to calculate critical moment, which specifically in Eurocode, there is no address to how to calculate it, at least by now. Perhaps in the next generation, we will see how it should be calculated according to the code. But many references are suggesting some equations, how to calculate them, and also very basic equations from even 19th century are available to be used. In this video, we are just focusing on one cantilever, of which at the tip free end, we are going to apply one load and slightly tilt it to one side and to check how we need to calculate the critical force. And also at the end, we will compare with some results from one book, and also we will see if we move or replace the force from the bottom to the top of the cross section, what would happen and how it would affect the buckling load. Assume we have a cantilever with the length of L at A supported by a fixed support, and at point B is subjected to the force P. And assume that we are talking about a cross section which is I section. For the force P, we have three options, and we will consider three options. It can be applied to the top, it can be applied to the centroid, and it can be applied to the bottom of this section. So let's say point B1, B2, or B3. Now, the idea for lateral torsional buckling is when the load cannot go further to its plane, it starts to move laterally. So starting to writing the total potential energy equation is from the moment that the beam starts to move laterally. It's lateral torsional buckling. As a result, the energy which is lost or which is stored inside the element is not considered until it starts to buckling laterally. First of all, let's have some coordinates. Let's say V is the displacement in the plane of the beam. And here we can assume it's the longitudinal direction of the element. As a result, if we look at the 3D view, this direction is V, and then the other direction is W. If we look at the cross section, this is Y, and the other one is zeta. So starting to moving laterally is the point that the element cannot go further to the vertical direction. It can happen for any single perturbation. It can be from the force, it can be from the material, it can be from the imperfection of the element. Whatever the reason is, at the end of going down in the plane of AB, if the load is increased and it cannot go down and it has a weakness in the other direction, so the beam starts to move laterally. What would happen if we look at the 3D view? So we have two options. It can shift laterally or bend laterally, and also it can rotate longitudinally, which is called torsion. In that case, we might have this type of deformation. So it is tilted or rotated around its longitudinal axis, and also it is moving toward outplane. So from that moment, we have two functions of movement. One is the rotation, the other one is the lateral movement. So I can say that omega x is the lateral deformation, and also rotation, I can name it phi x, torsional deformation. In other words, if I look at the cross section from the top, this is the lateral deformation, and if we look at it from the section, the rotation. Now starting to write the total potential energy to calculate what is the critical load is from the moment that the beam starts to buckle laterally. As a result, as mentioned earlier, we do not consider any kind of in-plane bending work externally, internally, loss of energy, gain of the energy, elastic energy inside the element, strain energy. They are completely ignored until it starts to buckle laterally. So we have starting point is the moment that the beam starts to buckle laterally. In that time, we will have omega x, which is the lateral movement. We have phi, which is the torsion. Now we can write down the total potential energy. I will be integration from 0 to L due to bending about weak axis. So it will be E I z omega x second derivative s square. Remember that Iy is working, but when it starts to move laterally, we write the equation from that moment. Before that, for sure, we have strain energy stored in the structure, but we want to calculate the buckling of the beam. As a result, that energy is neglected in the calculation. Plus GIT p prime x s square dx from 0 to L due to torsion. And also we need to consider the warping. Warping is also a kind of normal stress that can happen if the element is under torsion. So it will be 0 to L E warping moment of inertia times second derivative of phi dx. So these are the gain energy or the stored energy. And now we need to calculate what is the loss of energy. So the used energy or the lost energy is the energy that starts to move laterally. There is no force in that direction for sure, but because we have bending moment about y-axis, when it starts to move laterally, we have the effect of this movement. I think in 1940, there was a scientist named Winter who wrote a very nice explanation how to calculate the effect of force out of the plane of the bending and how to calculate what is the energy in that direction. So if you are interested, it is written in many books. It's negative because it's loss of energy and integration from 0 to L m about y times p prime times omega prime dx. Stored energy due to bending about weak axis, stored energy due to torsion, stored energy due to warping, and loss of energy due to the effect of moment about y-axis. There is one more that we need to consider if we assume that the element is rotated for phi. And if the force is applied at the distance of A from its centroid, immediately after starting to rotate, then we have two components of P, one in the direction of web, the other one perpendicular to web. P cosinus phi and the other one P sinus phi. And the distance of A is constant. Now we can see that this P sinus phi is starting to have a torsion about the centroid. In this case, if force is lower than the centroid, in this example, the centroid is exactly the shear center, it be considered as well. Torsion is in the opposite direction of the movement. As a result, this force is stabilizing the element. But assume that A is negative or the force is applied upper than the centroid of this cross section. Then the torsion will be in the opposite direction and it is helping the cross section to lose its stability. As a result, it's stabilizing the element. If it is in the center, then it's neutral and it doesn't have any effect. For this case, I assume that it's the lower and I use positive because it's helping the system. Later, we can play with the value of A to see how it affects. For the calculation of the energy, if we have the torsion and the angle of phi, then the energy is the area which is 1 over 2 t times phi. So it will be 1 over 2 t times phi. But this phi is subjected to the place that we have that force. In this example, it's at the distance of L. And t can be calculated as p sinus phi times A. As far as the rotation is very small, we can approximate sinus phi to be as phi. So this will be PA phi. And I can rewrite this as 1 over 2 p times A times p square. Now, to determine the answer of this equation, it is easier if we can find out the shape function of how it would buckle for omega and also for phi. If we look at the section from the top, in X and W or omega plane. And now if we sketch it as a line, it looks like cosinus. And we have to write down one admissible function for omega, which is, for example, here, a times 1 minus cosinus pi x divided by 2l. If x is 0, then omega is 0. And if x is L, then cosinus pi over 2 will be 0. And as a result, A will be the deformation in omega direction. Also, if we take the first derivative of this omega, it will be a function of sinus. And if x is 0, then a slope in this plane will be 0. So this is a good function to consider for omega. For phi also, we can assume something similar in a way that it starts to rotate and at the end it's maximum. So phi x can be written as p times 1 minus cosinus pi x divided by 2l. P at 0 is 0 and at L is maximum. The solution of the main equation, if we solve it by the moment equation for the element, the other method, you will see that we need to solve two differential equation with the order of 4 and they are coupled, and then we use some kind of decoupling methods to calculate them. So analytically, the solution of this might be completely difficult, but here is one example how we can use the functions or approximation for calculation. So necessarily these results might not be the best for fit calculation if we compare with FEM analyzers, for example. So the only thing that we need, we substitute these two functions to total potential energy function, and then as far as we are looking for A and B, then we make the first derivative of pi by respect of A and B, and then as far as it should be 0 like other examples that we had earlier, we form the determinant of the coefficients, and the determinant to have non-trivial solution should be 0. Then we can find out what P will be. So for this reason, we can use MATCAT. Omega as a function of x and L and A can be written as A times 1 minus cosinus pi times x divided by 2L, and B as a function of x and L and B can be written as B times 1 minus cosinus pi times x divided by 2L. Coming back to the notes, the bending moment, if we assume x is positive from left to right and the load is at the tip, the force reaction will be E with the moment of P times L. As a result, moment in the distance of x will be P times x minus P times L. So we need to consider this as the function of moment, m as a function of x and L and P will be P times L minus P times X. And I as a function of, as far as we make the integral between 0 to L, so X vanishes at the end, it will be a function of E and G and I of zeta, I of D torsion, warping, and what else? L, E, and also the distance from the center. A, what else? Nothing for now, so it will be 1 divided by 2 times integration from 0 to L times, for the function of E, I of Z times second derivative of V of omega by respect of X, X and L and A all together square dx plus this time G IT first derivative B, and this is S plus this time I omega or IW for the warping, second derivative of B yes plus, and then perhaps minus S. Now integration, this time it's round by round X, and the function will be M as a function of X and L and P times P as a function of X and L and B multiplied by first derivative of function omega. So if you are using MathCAD version 7, at least for this equation, I checked and it was not as I expected. So perhaps it is worthy if the derivative is taken by round m by respect of x times phi plus round phi by respect of x times m. At least for me, it didn't work. Plus 1 divided by 2 times P times A times, now we need to calculate phi at the distance of L. So phi at L and B square. So this function is a function of E, G, I, Z, I, T, I, W, L, P, A, and also A and B. Now, we need to take the first derivative of the function pi total potential energy by respect of the two parameters a and b. Very simple. Just take the derivative of function pi and also by respect of b. Now we need to form the matrix. Matrix will be a function of p, g, i, z, i, t, i, w, l, p, and a. So there will not be any a and b as far as we are forming the coefficient matrix. So it's a matrix with the degree of 2, and here is the a parameter, and this is for b. The same for a, here 3 over 4p and minus p pi squared divided by 16. So the same value is symmetric. And for b, can just remove parameters for a, and this is coefficients for. Now the determinant of matrix needs to be 0. From here it is easier if we solve by a cross section that we have the numerical solution. So let's go for one cross section. For example, IPE. We are looking for the moment of inertia about weak axis. E is 210 gigapascal. Poisson ratio 0.3. G is E divided by 2 times 1 plus nu. $80 gigapascal. And moment of inertia about z-axis is 2.836 10 over by 6 millimeter over by 4, and torsional constant 127.4 10 over by 3 millimeter over by 4. What else? Warping constant 3668 0 10 over by 6 millimeter over by 6. So we have IZ, IT, IW, and we need to assume one length. Let's say L is 2 meters. So now the solution is the determinant of this matrix to be 0. So I will write solution of P and A is determinant of this matrix. So now we can solve it for P for different A values, but it is also nice if we can sketch to find out how it looks like. So solution, and where this solution is 0, then it's the answer for the P critical. And this is P. It is better if we define P up to 200, And also, so here this is 0 millimeter. Here we can see that if A is 0, so here we can see that it can be about 200 or even a little bit more. So let's go with 500. And I can adjust this to be 0. We are interested in the p-value where this function becomes 0. Also, I can sketch this for another a value. So the section is IP 240. Assume that it goes to minus 120 millimeter. So here we can see that if we put the load above the section, then you can see that with very smaller value, it can buckle. Now, if we put it on the other side of the section, let's say on the bottom of the cross section, we can see that 5,000, right, 2,500. This vertical marker to see where it's 0, so 1,700. So we can see that when we put the load lower than the central of the cross section, so it starts to stabilize it. In FEM software, for example, in RFEM, when we are adjusting the setup, there are three options. The load is in the shear center, the load is below, or it's above. When it's up below, it is written that this is a stabilizing situation. And usually by default, as far as the load is coming typically from the top flange, it is by default on the destabilizing situation, meaning that it is in the side that it would destabilize the cross section when it buckles. In the software, we can adjust just the setting according to our need or our task, whatever it is. Here we can see that the load is 330 or 350 kilonewton when it is in the center, and also it's 82 kilonewton when it's in the destabilizing side or on the top of the flange. Also, we have this equation from the books that have been calculated with the Bessel functions earlier with the other scientists. This is from book Stability of Structures, SHAHgordi in 2011. P critical is divided by L square times E times by Z times G times by T. So it is 78 kilonewton, and we can see that it's very close to 82 kilonewton. But according to the calculation with the Maple cipher and also Bessel functions, this equation represents it's in the load is in the centroid. Also, there are some equations from Timoshenko calculation back to 1910 that a gamma value is suggested to be used. We can check from that as well to see how it looks like. So the equation is given by Timoshenko according to a gamma 2 value. So we can calculate gamma 2, which is a function of it's a very good approximation in my opinion, as far as it's relevant to also the length of the beam. So E times IW divided by G times IT. times L square. So here this value is 12, and then we can write down something similar. Instead of 4.013 or 120 something, we can use gamma 2, and the rest are same. 240 kilonewton. Coming back to our calculation, if we set this value exactly in the center, we can see that now this is closer to what we calculate. Also, we can use plate buckling analyzers in a software to calculate what the exact value of this buckling load will be. I can just add this for Timoshenko. So this value is 244 compared to 78, and here we can see that the results are very close for these two, and the other one is very far from what we calculated. I think that for better or more accurate calculation, we need to add some terms, for example, another terms of cosinus in the other formats, for example, a times 1 minus cosinus pi x divided by 2l plus another factor times 1 minus cosinus pi x 2 pi x divided by 2l and so on. Also, Fourier series would be a good option to solve this problem. So here, this is from equation from the stability of structures. SHAHgordi 2011, and this is from Timoshenko about 1910. And here is our approximation, 78.925. So in this SHAHgordi 2011 book, it is written that the load is in the center, but here we can see that our calculation shows that it is very close to when we put the load on the top. Perhaps the length is very important, and also the cross section. And from the Timoshenko, we can see that the equation is reasonably, let's see what's the difference, 343 divided by 243, it's about 40% greater than that. And also, if we increase the numbers of parameters, for example, A, B, C, and D, we can see that it will be closer to the exact and accurate value. And also, it can be modeled in a FEM software. Yes, in this example, we calculated the lateral torsional buckling for one cantilever beam supported at one end with a fixed support, and at the other end, it was loaded by a transversal load P. And from the state that it starts to buckle laterally, we calculated the total potential energy, and then we estimated two admissible functions for the calculation of buckling load. And at the end, we compared the result with the one book in 2011, and also with the given equation from Timoshenko in 1910. And in the next video, we will go through the post-buckling of a beam for lateral torsional buckling. But it will be done completely by software, and I will use RFEM for that. Thank you. See you in next video. Bye.